Hello, this is Dr. Christy Lukes. In this video, we're going to be beginning to look at what happens when we mix solids with liquids. So, if you take some sugar and put it in your coffee, right, until no more will dissolve and just one or two little crystals remain, that system is now a saturated solid-liquid system. If you change the temperature, you'll change how much of the solid will dissolve. So you could heat your coffee up and get more sugar in, and you could cool it down, make some iced coffee, and if you left it until it reached equilibrium, some of that sugar would crystallize out. The quantity that will dissolve is going to be called the solubility of the solid in that particular liquid. As I've been saying, that is available in Perry's handbook. So some of the things that you can find by perusing Perry's handbook is that you can dissolve 62.1 grams of arsenic oxide in 100 grams of water at 10 degrees C. And if you heat the water up to 40 degrees C, you can dissolve 71.2 grams in 100 grams of water. So all sorts of data is available in there. You just have to look for that information. But we frequently do things that are supersaturated. This is a metastable solution, okay? You've dissolved more in than is possible according to solubility. Now, usually what happens is that you have heated it and now you've cooled it down. And until it reaches equilibrium and the crystals drop out of the solution, you're going to find that you have this supersaturated mixture. This is the way that we make rock candy. I hope you've had the pleasure of making that experiment sometime in the past. If not, maybe this summer is the right time to do that. But you heat and dissolve in as much sugar as will be available, okay, to reach a saturated mixture at a very hot temperature, and then you cool the mixture and wait for the crystals to slowly form because you have a metastable, okay, supersaturated mixture. And so those crystals slowly form and you have some delicious rock candy. Another thing that happens with solids and water, or solids and any liquid, but in particular water, some salts will bond to water molecules when they form their little structures, and they end up forming something called a hydrated salt. Okay? Now, I like to think of this like a mama duck, okay? And a mama duck who has baby ducklings is never without her ducklings, and she's constantly ushering them around. They always stay just right there clustered around her. There are going to be certain structures and clusters that are going to be common for certain chemicals based on their molecular structure. When you're doing material balances, you treat it like a single molecule. So if you have one of these hydrated salts, and so here I've got the example for magnesium sulfate salts, you can have the form that has no water molecules. That's called anhydrous magnesium sulfate. Okay. And it's all magnesium sulfate, and if there is any water present, it's just going to be free floating. It's not going to be bonded to it. But you can also have magnesium sulfate bonded with a single water, or 6 waters, or 7 or 12 waters. Those are the structures that are possible. So again, it's like, here's your mama duck, and she's got 6 little babies that everywhere she goes, they're floating around with her. And it's going to depend on exactly what conditions you mix this water with your magnesium sulfate. Again, the best thing to do is just treat whichever one of these you have formed as if it's just a molecule. If you have 30 moles of magnesium sulfate, you have 30 moles of water that's being carried around with those particles, okay? Or down here on this one, you would have 12 times 30. If I had 30 moles here, I would have 12 times 30 moles of water molecules that are bound up with that. Okay. The next little odd topic associated with solids and liquids is colligative properties. Now, you may have encountered these in a chemistry class. We're going to do a very quick version of this because it is typically covered in some other courses. But basically, properties change when a pure liquid has a solid dissolved into it. And the ones that we're most interested in are vapor pressure and boiling point and freezing point. But osmotic pressure and some others also are changed by having these solids dissolved into the liquid. Now, it's going to depend on the molar concentration of the solute in the solution and not on what the solute is. Okay. The rules I'm going to show you are appropriate for non-electrolytic solutions. I'm going to work them for things like salt solutions, but that's really not the time they're most appropriate. It would be more appropriate if you dissolved, say, sugar into your water, something like that. But these are some estimation techniques. So these are just going to be for estimation. They're not going to be very precise. So, vapor pressure lowering. If I want to know the effective vapor pressure of a liquid after I've added some solvent to it, or added some solute to it, then I'm going to take the vapor pressure that I actually have and subtract off the vapor pressure times X, the amount of solute I added. So X is going to be mole fraction of the solute. Okay, now the solute would be like sugar dissolved in the water, something like that. It's going to be valid if I have a non-volatile, meaning it won't go into the gas phase, non-reactive, so no reactions allowed, non-dissociative mixture. So that's why, although I sometimes will apply this to salt, it really isn't a very good approximator for salt. It's better for something like sugar that does not dissociate. Freezing point depression is going to be very similar, okay? The solvent in the solution will freeze at a lower temperature than the pure solvent. If X is very small, then I can estimate the melting temperature of the solution by looking at the melting temperature of the solvent minus R, the ideal gas constant, times the temperature. And now remember, this has to be in Kelvin, or if you're using English system, then degrees Rankine. Okay, so an absolute temperature squared over delta H of fusion times that liquid fraction. Again, this is going to be the idea behind why we put salt on icy roads and sidewalks. This isn't going to be very correct for those because salt is going to dissociate when it mixes with the water. And then I also have boiling point elevation. The solvent in the solution at a given pressure will boil at a slightly higher temperature. So if I had a range from the melting point to the boiling point for the pure, for the mixture it's going to be slightly larger. Okay, the melting point will be a little lower, the boiling point will be a little higher. And in this case, it's going to be the boiling point of just the pure solvent, water, whatever it is, plus R times the boiling point squared. Again, make sure this is going to be absolute. Divide by the heat of vaporization times the mole fraction of the solute. So we'll do a little example here. Again, we're going to do it for NaCl because it's easy. Not very correct, but it's easy. So we want to consider 1 milliliter of NaCl dissolved in 1 liter of water. We want to see what that effect, not adding very much, right? 1 milliliter and 1 liter, so I'm adding 1/1000th. Okay, And I want to see what's going to happen to the vapor pressure, the boiling point, and the freezing point. So I need data for NaCl and for water. I've got the specific gravity and the molecular weight. I have for the water, I have melting and boiling point data with heat of fusion and heat of vaporization. So I found all of those in the appendix of our textbook. So as you go through and do this, I'm also going to remember, always need to know what is X, and X is the mole fraction of the vapor. So I have 1 milliliter of NaCl, okay, which is 0.037 moles of NaCl, added to 1 liter of water, which is 55.5 moles of water. And therefore the mole fraction is the amount of NaCl divided by the amount of total. So this is my mole fraction. So it's a very tiny addition. If we look at what's the change to the vapor pressure, well, I'm going to simply take 1 minus X times the total pressure. And so 0.9993. That total pressure in this case was the vapor pressure of the pure substance. So it's a small change to the vapor pressure. What about to the boiling point? Well, I need the boiling temperature and the heat of vaporization. This is going to be an addition. Probably the hardest thing is getting all the units to work. So just make sure that you're using the correct choice for R, that you're using absolute temperature, and that since if that was in joules and this is kilojoules, I corrected this to joules down here. So all the units have to cancel except for 1 Kelvin, right? So I'm going to add degrees to degrees. This is going to be a delta T in Kelvin, which is exactly the same as a delta T in degrees C. So I can add that to degrees C. The units are correct. And so in this particular case, it's a very small boiling point elevation if I have a solution that's non-dissociative, non-reactive, etc. Okay, so the predicted boiling point elevation is 100.02 degrees C. And the freezing point depression, similar kind of situation, again checking all the units, and we find that it's negative 0.07 degrees C. One last topic. This is on adsorption. Adsorption is kind of an odd topic. A lot of times chemicals are going to preferentially stick to the solid rather than remaining in the gas or liquid phase. So places where you might have used this is if you put baking soda in your refrigerator, it will absorb the odors. In my aquarium, I put activated carbon in the aquarium and run the water over it, and it absorbs the ammonia and the organic waste that the little fish puts out. Now the word here is adsorption, not absorption, so D, not B. Okay? Adsorption is when a substance adheres to a surface, so a solid surface. The concentration of the fluid is on the surface and it's not internal, it's not dissolved in somehow. Absorption with a B is when a fluid is dissolved into a liquid or a solid, but the fluid changes the liquid or the solid and it's dispersed throughout. So I have little pores, okay, inside my solid surface, the activated carbon, whatever, and my substances stick to all these surfaces here. This is adsorption. If it's absorption, then it's like being dissolved into the liquid, so it's changing the property of the solid. Okay? In adsorption, some vocabulary. The solid, in this case, is the adsorbent, and the fluid that sticks to the walls is the adsorbate. I want to briefly introduce you to adsorption isotherms, because most of the time if you're talking about adsorption, you are going to do data for a fixed temperature. Therefore, iso meaning the same, therm, meaning temperature. And so we'll do this for a fixed temperature, or we'll do an isotherm. The adsorption isotherm is going to be the maximum mass of adsorbate that could be held by a unit of adsorbate. So that activated carbon with all those little porous structure there. This data here is showing you how much could be absorbed, how much carbon tetrachloride, for instance, could be absorbed per gram of carbon. There are some typical forms that seem to describe the data that one takes in a lab. And the one that is most frequently used is going to be the Langmuir Isotherm equation. And in that particular case, okay, what we find is that we have this constant K, which is the adsorption constant, okay, and it ends up looking something kind of like this here. But the key thing is that if you look at the mole fraction that could be absorbed versus the pressure, the partial pressure of what's in the gas, you're going to find that it's going to be a curve that will look very much like this. This is characteristic of many, many adsorption systems, okay? And it's, again, called the Langmuir isotherm. But there are going to be some other cases. For instance, if you just limit yourself to only looking down in this region of the graph at very low concentrations, it looks pretty much like a straight line. And so we can use that. Again, this is just simply a way that one can determine how much could be absorbed by a certain system. So in this little lesson of videos, we just kind of quickly hit a lot of topics about mixing solids and liquids. Be sure to look at the examples in the textbook before you move on.